Based on the syllabus, we are going to cover section 3.7 today, all right? What do we learn in section 3.7? 3.7 and 3.8 are the last two sections of chapter 3. Those two sections are about arguments in logic. Let me give you the definition. Argument in logic is kind of related to, but pretty different from the argument we mention in real world scenario. When you say someone just had an argument, that argument is, is different. In logic, in order to be an argument, it has to satisfy a certain conditions. All right, let me give you the definition of an argument in logic. An argument in logic contains bunch of statements, and those statements form into two parts. So an argument has two parts. The first part includes one or more premises. We can write premise 1, premise 2. The argument could have more premises, but for convenience, I'm gonna only write 2 of them. All right. So let's say this argument has 2 premises, premise 1 and premise 2, and I put them above a horizontal straight line or line segment, above a horizontal line segment. And below the line, we're going to have the second part of the argument. The second part of the argument is the conclusion of the argument. Conclusion. All right. So an argument contains 2 parts. The first part is the premises. It includes one or more premises. And the second part of an argument is the conclusion. And the 3 dots here means therefore. Sometimes we don't even write the 3 dots. With the horizontal bar, we won't have any confusion. So basically, above the bar, premises, below the bar, conclusion, and that's it. I can give you an example. Let me give you an example of an argument in logic. If I take care of the plant, then the plant survives. That's the first premise, first line. And second premise, start a new line. The plant died. And draw a horizontal line to separate the premises and the conclusion. Conclusion is I did not take care of the plant, right? So I do not use the dot, or it's optional, okay? The bar actually is sufficient to show the structure of an argument in logic. Let's analyze the structure of this argument. Above the bar, we have 2 statements, okay? We can write the first statement as P. The first statement can be, actually the first statement is a compound statement. I'm talking about if I take good care of the plant, comma, then the plant survives. The first premise is a compound statement. It is a conditional because the structure is if, comma, then, right? So if we let I take care of the plan as P, it is a simple statement, right? And I let Q to be the plan survives. The plant survives. Then we can rewrite this argument in its symbolic form. You know, an argument contains a bunch of statements. If we use letters to represent the simple statements in the argument, then we can write the argument in its equivalent symbolic form. So here, I let P be I take care of the plan. I let Q be the plan survives. Then the argument can be written as this way, okay? The first premise, I can write this way. Premise 1, premise 2, conclusion. Okay, so above the bar, the first line, premise 1, if I take care of the plan, comma, then the plan survives, that's a compound statement, conditional statement. That can be written as P implies Q. The first premise in the argument is a conditional statement, P implies Q. If I take good care of the plan, then the plan survives. The second premise says the plan died. The plan survives is Q. Then the plan died means it didn't make it, right? Does not survive, did not survive. Then we can use the negation of Q to represent it. So the second premise, we can use the negation of Q to represent it. And the conclusion, says I did not take care of the plan, and that's the negation of P. So we can use the negation of P to represent the conclusion. So this part is the symbolic form of the argument. All right. Okay, the point here is you need to know what does an argument in logic look like. It has two parts. The two parts are divided by a horizontal bar. Above the bar, we have a bunch of statements represent those premises. And below the bar, we have the conclusion. And the conclusion is drawn based on the premises. So how do we, express the argument a better way that you really understand what's trying to say, this statement? So if I suppose if I take care of the plant, then the plant survives. And also suppose the plant died now. Those are two conditions, right? Two premises. Now I can draw the conclusion that I did not take good care of the plant. Do you guys have any questions so far about the structure of an argument in logic? Above the bar, we have a premises. Below the bar, we have the conclusion. Both the premises and the conclusion are just statements we have learned in previous sections. We have learned a lot of things about statements, right? Okay, thank you, Ashlyn. Well, now we know what is an argument, and what we need to know about an argument. We need to know how to evaluate. How to evaluate an argument. All right. There are two criteria. There are two criteria that we can follow to evaluate an argument. The first criteria is called validity. The second criteria is called soundness. All right. The first criteria that we can use to evaluate an argument means, is this argument good or bad, strong or weak, right? We have a standard, we have a criteria, it's called validity. We have another criteria, it's called soundness. Let me explain what is the validity of an argument and what is the soundness of an argument. We say an argument is valid. We say an argument is valid if the combination of the premises directly lead to the conclusion. So validity is only about logic. When we say an argument is valid, that means suppose premise 1 is true, premise 2 is also true, then logically we have the conclusion is true. Means whatever above the bar can directly cause the conclusion below the bar to happen. Then we say the argument is valid. Again, validity is just a pure logical concept. We only consider the logic. So otherwise we say the argument invalid. Invalid means if premise 1 is true and premise 2 is also true, not necessarily lead to the conclusion is true. So logically, if the premises are true, not necessarily cause the conclusion is true, then we say the argument is not valid, and we say the argument is invalid. An invalid argument is called a fallacy. Okay, so an argument is either valid or invalid. If an argument is invalid, we say the argument as a fallacy. Fallacy is a new terminology for us. Fallacy refers to an invalid argument. An argument is invalid means even when all the premises are true, even we suppose all the premises are true, but logically, we do not have the conclusion true necessarily, okay? It doesn't directly cause the conclusion to be true. So that is invalid. An argument is valid is as long as all the premises are true, we can directly have the result that the conclusion is true. Is that clear, guys? Does that make any sense? What is validity of an argument? How do we know if an argument is valid? How do we know an argument is invalid? Am I clear about that? Okay, thank you. Thank you for letting me know. Very good. So that is one criteria to evaluate an argument, right? When we say argument is valid, that means all the premises true can directly lead to the conclusion is true. When we say an argument is invalid, means even all the premises are true, not necessarily lead to the conclusion is true. And another criteria to evaluate an argument is the soundness. Soundness is more strict, okay? In order for an argument to be sound, the argument has to be valid first, okay? Let's say we have a valid argument. On top of that, all those premises are facts. All those premises are true, okay? Then the argument is a sound argument. Let me repeat it. What is a sound argument? Firstly, the argument is valid, means suppose those premises are true, then we can directly lead to the conclusion is true, logically. On top of that, all the premises are also true. Then that means the conclusion is also true, also represents a fact. Then that argument is sound. Okay. When we say an argument is valid, we do not need to require the premises are true. They could be both false. It doesn't matter. Even they are false, we only care about suppose they are true. And they can logically lead to the conclusion is true. Let me know if I'm clear here. So what's the relationship between validity and soundness? I can show you this way. Soundness or sound arguments is a subset of valid. Right this way. Sound arguments is a subset of valid arguments. Valid arguments. All the sound arguments, they are valid, but a valid argument is not necessarily sound. Yeah, the sound argument, to make an argument sound, we need a, higher standard. Any questions, guys, so far? That's how do we evaluate an argument. Does that make sense? Guys? Okay, very good. Then do you want to know if my example, the example I gave you, this argument, do you want to know if this argument's valid? Our class mainly focus on validity, okay? Our class, this section, mainly focus on validity. And the soundness is pretty simple. Once you know it is valid, and you just need to check if the first premise tells a fact, if the second premise also tells a fact. If they both are telling facts, then the valid argument is also sound. Okay, now we are going to evaluate or test the validity of this statement, of this argument, I'm sorry. Test the validity. Test the validity of the following argument. That's the main thing we need to do in section 3.7 and section 3.8, the last two sections of this chapter. Test the validity of an argument. In section 3.7, we learn one method or a tool. We need to grasp a tool. In section 3.8, that's going to be on Monday. Next Monday, we learn 3.8. We're going to learn another tool, all right? In 3.7 today, the tool we are learning to test the validity of an argument is the truth value table, okay? Test the validity of the following argument by using the truth table. The previous two sections, 3.3, 3.4, we have been, talking about truth table, right? And how do we use the truth table to test the validity of an argument? Firstly, we have to rewrite the argument as its equivalent conditional statement. We know the truth value table is to determine the truth values for a compound statement, right? In fact, the argument can be written as a conditional statement. Let me show you. Let me mark this again. This is a premise number 1, the first line. And this is a premise number 2. Again, the argument could have more than just the 2 premises. But for convenience, we use 2. All right. I think in our homework, everything, we mainly have arguments containing 2 premises. And the statement below the bar is the conclusion. May I have your attention, guys? Let me show you how do we rewrite this argument as a conditional statement that we can test the validity using the truth table. This is how. We firstly write the first premise. This is the first premise, right? I use a parenthesis to frame it. And I take the conjunction of the first premise and the second premise. The second premise is not Q. All right, do you see that? And then implies the conclusion, not P. You see that? That's how you translate or rewrite an argument as its equivalent conditional statement. Let me repeat, what are we going to do? What are we trying to do here? We are rewriting the argument as a conditional statement. Conditional statement contain this symbol, right? And the antecedent is the conjunction of all the premises. As you can see in this example, first premise, P implies Q, and second premise, negation of Q. So the antecedent is the conjunction of all the premises. And the consequent is the conclusion, not P. And if we use the truth table to determine or to find the truth values for this compound conditional statement, and we find out this conditional statement is a tautology, means this conditional statement is true in any cases or always true, then we can conclude the original argument is valid. Do you see the idea, everybody? Do you see how did I rewrite the argument as a conditional statement? How did I find the antecedent? How did I find the consequent? And what's the idea? By using this conditional statement to determine the validity of the argument. Am I clear, everybody? Okay, very good. Then let's create the table. Let's create a table, right? It only has 2 statements, simple statements involved. So the first 2 columns must be P and Q. And the last column must be the conditional statement. It's very, very long. Okay, I'll read it, even it's very long. It is P implies Q and not Q implies not P. Okay, so that's our target statement, right? Target statement. I'm gonna use my color scheme. And I'm gonna use green. How about green to color the antecedent, and use blue, purple to color the consequent, all right? And I want the two columns preceding the last column as the antecedent and the consequent. So P implies Q and not Q, right? So as you can see, this is the consequent of our conditional. And this column is the antecedent of the conditional. So ideally, we want them next to each other, right? Antecedent, consequent, and antecedent implies consequent. All right, and the green is a conjunction, right? The green is a conjunction. We would need not Q, right? We need a not Q here. We also need a not P. So how about we put not P here, not Q here, and the P implies Q here. And that should be enough, okay? That should be enough. P implies Q. Okay, I'm gonna reorder it. I'm gonna do P implies Q here, P implies Q here, and then not P here, and then not Q here, right? Yeah, we have everything. We have everything. Let me label column 1, column 2, column 3, column 4, column 5, column 6, column 7, column 8. And we have 4 cases because there are only 2 simple statements involved. Let me make this a little bit narrow, just enough for T and F. This case 2, this case 3, and this case 4. All right, case 2, case 3, case 4. At this point, you should be very familiar with the first 2 columns in the table, right? PQ, the 4 cases are T, 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 F, F, T, F, F, right? F, F. And let's fill in the truth values for those columns. The column 3 is the P implies Q, a condition. And the antecedent is column 1, consequent is column 2, and then P implies Q as column 3. So this is the ideal design. Antecedent, consequent, antecedent implies consequent, right? So this is conditional. What's the sentence that I made you to memorize regarding a conditional? Do you guys remember? Do you guys remember Bobby? Let me write it here. The sentence we need to remember about the conditional is the only case in which a conditional is false is when the antecedent is true, but the consequent is false. I have repeated this many times. It's very important, guys. All right, I hope you know this. There's only one case. Trust, yeah, exactly. Thank you, Ashlyn. Trust friends forever. Exactly. Perfect. Let's see, do we have a trust friend? We are looking at the first 3 columns, right? Now we are considering the first 3 columns. Let's see if we have trust friends. T, okay, T, trust friends forever, right? And all other 3 cases are not trust friends, so temporary. There we go. We have column 3 taken care of. Column 4, column 5 are negations of PQ, so I believe you can do that, right? I'm gonna do column 4 and column 5 quickly. Column 4 is a negation of 1. Column 4 is a negation of column 1, right? Negation of P. The yellow, we are going to negate the yellow. Yellow is T, so F, T, F, F, T, F, T. There we go. Column 5 is the negation of column 2. Negation of Q. Q is yellow right now. Okay, Q is yellow right now. Negation of Q. When Q is T, F, Q is F is T, Q is T is F, Q is F, this is T. Done. Now let's look at the column 6. Column 6. Column 6 is a conjunction. You know, I use a parenthesis. Even in some cases, without the parenthesis, there's no confusion. For example, this parenthesis actually is not necessary, but I like to use a parenthesis because the structure will just be even more obvious. All right, so this is a conjunction for sure. The conjunction has two pieces, remember. One is to the left, the other is to the right. Can you see which two columns are the two pieces in this conjunction? To the left of the conjunction symbol, we have P implies Q. To the right of the conjunction symbol, we have negation of Q. So do you see which two columns are the two pieces in the conjunction? Do you see it? Do you see it? Exactly. Awesome. Thank you. Thank you, Jennifer. Thank you, Ashlyn. Thank you for paying attention. You guys are great. Exactly. Column 6 is column 3 and column 5. Okay, so I'm going to use the color scheme. Column 3 and column 5. And we are going to take the conjunction of those two yellow and to determine the values in column 6. Column 6 is a conjunction. What's the sentence? I'm going to type the sentence again. The only case a conjunction is true is when both pieces are true. Conjunction is high maintenance, right? Keep a very high standard. Yeah. So we have a conjunction. So in order for the only case the conjunction is true is when both pieces are true, right? No, not both true, not both true. Yeah, this one, TF, not both true. FT, not both true. TF, not both true. TT, okay, finally. We get a TT, so this case 4 is true. That means all other cases, F, F, F. Okay, we have column 6 taken care of, right? Now let's do column 7. Well, as you can see, column 7 actually is just a negation of P, and it's the same with column 4. Do not be afraid having repeating columns in a table. Sometimes we repeat a column just to make our job easier. The design looks better. You won't feel burdened because column 7 is the same with column 4, and you just copy it, right? You just point column 4. This is F, T, T. Yeah, everybody know how to copy things, right? Just do exactly the same thing. Now we are ready for our conditional. That conditional statement in column 8 is equivalent with our argument. Yeah, don't forget we are doing argument. Yeah, so far, right now we are doing the table. Seems like nothing new, right, from the previous sections. But actually, we are doing argument. Then column 8 is a conditional with antecedent green, column 6, and the consequent purple, column 7. So we have the ideal order: antecedent, consequent, and a conditional. That's how did we design when we create a table, right? All right, what's the sentence? The only case in which a conditional is false, Bobby's case, is when the antecedent is true, but the consequent is false. We are looking for trusted friends. Trust friends. No, not trust friends. Not trust friends. Not trust friends. Not trust friends. There's only one trusted, but this is not friend, right? Okay, so we do not have forever. We do not have forever. We have T. In all cases, column 8, this conditional statement is true. That means this conditional statement is a tautology. Well, you do not have to struggle with terminology. If the conditional statement that is equivalent to the original argument is true in all cases, T, then we can make our conclusion now. We have our decision. We have our result of the test. The task here is to test the validity of the argument, right? The argument is valid. Okay, the argument is valid. The argument is valid because we use the truth table. Proved the argument's equivalent conditional statement is true in all cases, always true. That means it doesn't matter P is true or Q is true or P is false or Q is false. It doesn't matter. When premise 1, suppose premise 1, premise 2 both happen, then logically we can directly lead to the result that conclusion happened. And that guaranteed the validity. It is valid. Am I clear, guys? Am I clear, everybody? That's how do we use the truth table to test the validity of an argument. Perfect. Thank you, Charlie. Thank you, Ashley. What if the last column end up with not all T? It has at least one F. Then that means those premises do not necessarily lead to the conclusion. Then logically, the argument is invalid. Okay, only when the conditional is true in all cases it is valid. Even just the one false here is invalid. Okay, and you know this is actually has a name. This valid argument. This valid argument has a name. It is the contrapositive reasoning. Do you guys remember contrapositive? Do you guys remember what is the inverse? What is the converse? What is the contrapositive? If you take notes, you might be able to find it in notes. Let me see if I can quickly find our notes. It might take a little bit of time because I have everything in the same. I think I can just use the time to write them again. Let's review what is inverse, converse, and the contrapositive very quick. P is I take care, plant. Q, plant survives. Just some simple keywords. This is P implies Q, all right? Is the original statement, conditional statement. And let's review what is the inverse, what is the converse, what is the contrapositive, all right? The inverse of the original statement is not P implies not Q. Means we negate both antecedent and consequent. We negate both. And number 3 is the converse. The converse of the original statement. All right. It is a Q implies P. Q implies P. And what is the contrapositive? Contrapositive of the original statement. It is not Q implies not P. I hope you still remember. And then we also have already learned number 1 and number 4. The statement and its contrapositive. Number 1, number 4 are contrapositive of each other. the order of the antecedent and the consequent are reversed. Also, both pieces are negated. So number 1, number 4 are contrapositive of each other, and they are equivalent. They are equivalent means they are either both true or both false. They are equivalent, and those two are equivalent. If the original statement is true, its inverse is not necessarily true. Its converse is not necessarily true either. Okay, for example, our P, I take care of a plan, then my plan survives. That is true, right? If I take good care of my plan, then my plan should be able to survive. But its inverse is not true. If the plan survives, then I take good care of the plan. Maybe the plan is just strong, like a cactus. I don't have to do nothing, it could survive, right? Not necessarily true. So the plan survives is not necessarily mean I spend my time to take care of the plan. So if the original statement is true, does not necessarily have the converse is true either. So here the converse says, oh, sorry, I messed up. So the inverse is negate both. So if I did not take good care of my plan, then the plan did not survive. If I did not take good care of the plan, then my plan did not survive. It means if I do not take care of my plan, the plan will die for sure. Not necessarily, right? Maybe cactus is very strong. It's same with the converse. The unconverse not necessarily true. If the plan survives, then I take care of the plan. Not necessary, right? But it's a contrapositive is always true. If the plan die, then that means I did not take good care of the plan, right? So this argument is called the reasoning of a contrapositive. P implies Q. If P is true, then Q is true. Now Q is not true. That means P is not true. You see that? Try to make sense of it. If P directly caused Q, but now Q did not happen, then that means P doesn't happen either. Because if P happened, then Q should happen as a result. You see the reasoning? It's called the reasoning of a contrapositive. Let me do it again. Yeah, your conclusion is below the bar. If P happens, directly cause Q happens. Suppose that is true. And now we also know Q doesn't happen. Then we can make a conclusion. P does not happen. Because if P happens, based on the first premise, Q should happen as a result. But now Q doesn't happen. That means P does not happen either. Do you see the reasoning? It's called the reasoning of a contrapositive. Yeah, we have perfect. Thank you, Jennifer. Thank you, Ashley. We have a table in the guided note that mention reasoning of a contrapositive. Let me show you where the table is in the note. It's right here. There's a lot of information in this table. A lot of information in the table. This table gives 8 good examples. The top 4, they are valid arguments, or they are 4 important valid arguments. Since they are valid, we can call them reasoning. And the one we just proved, is this one, contrapositive reasoning. Is this one, the second one on the top. All right? Is the second one on the top. The 4 on the top, they are valid. Direct reasoning, contrapositive reasoning, disjunctive reasoning, transitive reasoning. And then we also have 4 common invalid arguments. They are 4 common fallacies. Remember, fallacy refers to invalid arguments. They are fallacy of converse, fallacy of inverse, misuse of disjunctive reasoning, and misuse of transitive reasoning. I don't think we have time to prove all of them. Right now we have half an hour left. How about we do this one? Okay, how about let's do this one? As a practice, you should use the table, truth table, to check all the 8. This is in the homework, the table, Crystal. This is in the homework. Yeah, exactly. It is in the homework. I mean, it's in my lab math. The system give you the formulas and tables when you need it. Will we need to know the difference and name each for the test? I think I would be able to answer this question when we review for exam 1. It's good if you know all of them. As I mentioned earlier, it's good if you can prove all the 8 arguments. Prove the 4 on the top, they are valid. Then the truth table should have a tautology in the last column, right? And the bottom 4, they are invalid. That means the truth table should not have a tautology in the last column. So when you practice those, then when you take the test, it will help you. You will have this table in the system, so you don't have to memorize. But if you understand those reasonings and the fallacies, it will just make your job for this section easier. Yeah, okay. I think I answered your question. Okay, let's do this one. The argument here has 2 premises. Premise 1, premise 2, conclusion. Premise 1 is P implies Q. Premise 2 is Q. And conclusion is P. I think I understand a little better. That's good. That's good. And this is the first time you see this type of things, and you already understand it very well. I think you guys are doing a great job. I'm familiar with those things because this is my job, and I have done this for so many years. But this is the first time you guys see this type of thing. If you it seems like not very familiar, it's totally normal. Totally normal. Honestly, we don't really use them in real world. So we only see them in this course. And I think you guys are doing great. If you encounter some challenging problem, do not, beat yourself up like this is difficult, I cannot do it. You need to know some problems are challenging, and you are doing a fantastic job because this is new to you. All right, there's a way to grasp the course, and you just need to understand each piece. Okay, if you have a question that is challenging, break it down into pieces, handle each piece at a time. Let's continue work on this argument. Let's firstly, how do we use the truth table to test the validity of this argument? We firstly rewrite the argument as a conditional statement. All right. The antecedent is going to be premise 1 and premise 2, right? Premise 1 and premise 2. The consequent is the conclusion, P. Done. That's it. You can do it, right? Yeah, the translation is not that difficult. the conditional statement looks like long, probably very long, like this, but it just have two parts. The first part is the antecedent. The second part is the consequent. So here we have P implies Q and Q implies P. I'm gonna use the same color scheme. How about that? Green is the antecedent. What is the color I use? Purple is the consequent. And I want the consequent right next to it, and I want the antecedent right next to the consequent. P implies Q and Q. All right? So the antecedent, this is the consequent, this is the antecedent. When we learn something, we focus on learning the methods. When we learn the topic, we focus on learning the skill, the method. Then when the number of the question vary, you still know how to do it. When we learn mathematics, we are not learning just one question. And if I change your number in a question and you don't know how to do it, then that be the purpose, right? When we learn something, we focus on, oh, okay, you heard about fishing, what is that called? Teach someone how to fish is better than give the person a fish, right? So we are learning how to fish. Okay, so we need a P implies Q. We need a P implies, this one is better because this one doesn't have negation. We won't have too many columns. And this is a Q, this is a P. Yeah, is a smaller table here. And then we have case 1, case 2, case 3, case 4. Case 1, 2, 3, 4. And column 1, column 2, column 3, column 4, column 5, column 6. The first two columns, as always, they are T, 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 F, F, T, F, F. Okay, column 3, P implies Q. Column 1, antecedent. Column 2, consequent. Column 3, is a conditional. Do we have a trust friends? The second one is trust friends, right? Trust friends forever. Not trust friend temporary, not trust friend temporary, not okay. So other 3 is temporary, right? Just like that. And number 4 is the conjunction of 3 and 2. Okay, let me write it down. Number 4 is the conjunction of 3 and 2. I'm going to color them as yellow. Then we know where to look. The table has a lot of information, right? Look at those two columns. We are going to take the conjunction of those 2 columns and get a conjunction in column 4. For a conjunction to be true, both 2 pieces have to be true. TT, okay, TT, here we go. Not both true, not, oh, okay, TT, another TT, right? T. So this is F, this is F. For a conjunction to be true, both 2 pieces have to be true. We have 2 cases here, case 1 and case 3. Both 2 pieces are true, so the conjunction is true. P, column 5, is the same with column 1. And we just need to rewrite those, right? Copy. Exactly. It is. All right. Finally, now we can look at the last column, the conditional we wrote that represent the given argument, right? Trust the friends forever. Column 4, antecedent. Column 5, consequent. Column 6, the conditional. We are looking for trust the friends. No. Trust the friends. No. Here we go. Trust the friends forever. Other cases, T, T, T. So the conditional statement is not always true. It is not a tautology. It is not always true means for this argument, the premises do not necessarily cause the conclusion to happen. So this argument is invalid. It is a fallacy, and a fallacy is called a fallacy of converse. Why? You can see. Suppose if P happens, Q definitely happens. But now Q happens. Can we say P also happen? We don't know. You see what I'm talking about? It not necessarily cause P happen. P implies Q does not mean Q implies P. We understand this is false, right? If you understand the fallacy of converse, for example, in your Pearson MATLAB math, if you see a fallacy of converse and the question say, use the truth table to determine if it's valid and invalid, and you don't have to do this work because you know I can identify this is a fallacy of converse. Since it's a fallacy of converse, it's invalid, and you save your time. You see what I'm talking about? Yeah, to answer Jennifer asked the question, right? Yeah, to answer Jennifer's question, do we need to know those? The more you know, the easier the homework is to you, right? The more you know. If you only know the basics, then every time you have to spend time to derive the result. But if you know all those reasonings and you can tell, oh, this is a reasoning and that is a fallacy, then you do not have to use those tables. I think, okay. Does that make sense, everybody? So we use the tool of truth table. Yeah, we use the tool, sorry, what's wrong with me today? My English is a little bit off. We use the tool of truth table, tested two arguments. The first argument is valid, and it's actually the contrapositive reasoning. The second argument, we proved it is invalid, and it's actually a fallacy. It has a name. It's the fallacy of converse. P implies Q not necessarily has Q also implies P. So when Q happens, we don't know if P happens or not. So we cannot make the conclusion. So this is invalid. The premises do not cause the conclusion happen. So it's a fallacy. It's called the fallacy of converse. Means the other way around, not necessarily true. Let's look at the table. Let's make a sense of those reasonings and fallacies. Let me make it bigger. I can just make this bigger. Direct reasoning. Okay. Premise one. Like suppose P happens directly cause Q happens. Now we know P happened. Then we know Q must happen. This is valid. It's called direct reasoning. It's very direct, right? Yeah. Suppose we know P happens directly cause Q happens. And now P happens. Then Q definitely happen. It's going to happen as a result. Do you see the direct reasoning? Do you see the direct reasoning? Let's say you know a couple. The couple has very good relationship. You know, if you see one, you will see the other because they are always together, right? So if you in a store, you see one person of the couple, and you know the other one is in the store as well. Kind of like that, direct reasoning. Very direct, right? Perfect. So if you see something like that in Pearson, and the question asks you to use a truth table to determine is valid or invalid, you don't have to do that. And you know it is definitely valid because it's the direct reasoning, right? Suppose P happens always cause Q happen, and now P does happen, then Q must happen as a result. So direct reasoning is good to know this. Counterpositive reasoning, we proved that is valid. Let's make sense of it. Suppose P happens always cause Q happens. Now Q does not happen. We know P does not happen either, because if P happens, then Q should happen, but now Q doesn't happen. You see the logic here? This is called a counterpositive reasoning. All right. The next one is called disjunctive reasoning. Yeah, let me copy paste this one. Let's understand one of them. And the other is the same thing, okay? Because you can switch, interchange P and Q. Let's make sense, because I don't really want to spend time to make a truth table. It's very time consuming. I give you 2 examples. I think that's enough. The first premise 1, says, we know P happens or Q happens. Means the premise 1 says PQ at least one happen. PQ at least one happens, right? And the premise 2 says P does not happen, right? P does not happen. Yeah, basically the 2 premises give us 2 pieces of information. The first piece of information says P and Q at least one happens. And let me tell you the 2 things, at least one happens. P and Q at least one happen. And we know P does not happen. 你给上 P, right? P does not happen. Does that mean Q definitely happens? Yes or no? If we know P and Q at least one happens, and P does not happen, then the one must be Q that happens, right? Q must happen. Otherwise none of them happen, then we do not have P or Q, right? You see that? So this is valid. Okay, very good. And this valid argument is called disjunctive reasoning. And same with this one, just to switch the order. So suppose we know PQ at least one happened, and Q did not happen. Then the one happens must be P, right? Yeah, same thing. And then transitive reasoning. Transitive reasoning is also very, very straightforward. I mean, very intuitive. Very intuitive. Let me explain. The first piece says P happens, always causes Q happen. And the second piece says Q happens, always causes R happen. So can we make the conclusion that P happens, always cause R happens? Transitive reasoning. If P happens, cause Q happen, and Q happen, cause R happen. Then if P really happens, then R will happen as a result. Isn't that very intuitive, right? And this part is just a counterpositive of this one. Suppose now R does not happen, then we know P does not happen either, because if P happens, then Q would happen, and Q happens will lead to R happens, but R does not happen, so we know P does not happen. I hope you are not having a headache right now. Isn't this very intuitive? You guys have any questions, please? Is this clear, guys? Transitive reasoning. Okay, perfect. Oh, Riz. So if you miss the roll call, please remember to email me, okay? So now let's look at the 4 fallacies. And let's look at the first one. It's called the fallacy of converse. We actually proved this one, right? We proved this one. The first piece tells us P happens always causes Q happens. Yeah, that's what we know. And the second piece says Q happens. Q happens. Would that, can we draw the conclusion based on those 2 pieces of information? Can we draw the conclusion P happens? Not necessary, right? P happens would cause Q happen. But now Q happens. We don't know if P happens or not. We cannot make the conclusion Q happen implies P happen. So this is the fallacy of converse. Right? And the second one is called the fallacy of inverse. As a practice, you can use a truth table to test the validity. And we'll tell you in which case is not true. So the first piece says P happen always cause Q happen. But now P did not happen. P did not happen. Can we say Q does not happen? For example, if it's raining, it is raining. Q is grass is wet. All right. So we know if it is raining, then grass is wet. But now the grass is dry. The grass is dry. Can we say, oh, sorry, my bad, it's not grass, not P. So the second piece is not P. So now we know it is not raining. It is not raining. Can we say it is dry? The grass is dry. This means it is not raining. It is not raining. So suppose we know if it's raining, then the grass definitely is wet. But now we know it is not raining. Does not guarantee your grass is dry? No, because someone else could just water the grass, right? So not necessarily. So this is a fallacy of inverse. Fallacy of inverse. No cause the grass can be wet from the water. Yeah, exactly. Thank you. Thank you, Ashley. Very good. Next fallacy is the misuse of disjunctive reasoning. Let's do one, and the other is similar. Let's look at this one. The first piece of information, the first premise says PQ at least one, at least one of PQ happens. The second premise says P happens. Then can we say Q does not happen? We can't, because or here is inclusive or, all right? PQ at least one happen includes both happen. You know, so PQ at least one of the PQ happen means either P happen, Q doesn't happen, or Q happen, P doesn't happen, or both PQ happen. So now we know P happens. P happens does not prevent Q from happening. It's possible Q happens as well, right? You see that? It could be both happen, right? It could be both happen. To find an example, we can think about it to see if we can find an example that can model this situation. At least one happen. At least one. So in the set theory, I use the example, the target, region A, region B, right? And to get a stuffed animal as a reward, and you have to throw the dart in region A or region B, right? Region A or region B. So now we know the dart is in region A. Now we know someone get the stuffed animal. He hit the region A. But that does not necessarily mean region B is not get hit. It could be here, right? In that case, both AB region, the dart hit both regions. It could be one example. Maybe you can find a better one. Please share with us once you figure it out. And the last one, misuse of transitive reasoning. And this one is pretty intuitive for transitive, fallacy of transitive. The first piece information says P happens will cause Q happen. Second piece says Q happen will cause R happen. But can we say R happen would cause P happen the other way around? Not necessarily. No guarantee, right? Example, let's say P, I study hard. Q, I pass class. R, I get a gift. Pass the class, I'm happy. Okay, I'm happy. Okay, let's say if I study hard, then I pass the class. If I pass the class, then I'm happy. So now we only know I'm happy. Would you make a conclusion I study hard? Maybe I'm happy for some other reason, right? You see what I'm talking about? Yeah. Please explore possible examples and we can share in the class. I want to check with you. So far, so good, everybody? About the 4 reasonings and the 4 fallacies? Perfect. All right, very good. And we have 5 minutes. Let's see what else on the. How about you do an exercise? How about let's do the exercise of translating. Use the standard forms of valid arguments to draw a valid conclusion from the given premises. You exercise or you do not feel energized. I do not exercise, therefore. What do you think? You exercised or you do not feel energized. So what do we put here to make a valid conclusion? So let's see. Let me enable editing. Okay. If we let P be exercise, Q be feel energized. Okay, then we can translate the given argument as the first piece of the first premise. You exercise or you do not feel energized. Exercise or not feel energized, right? 你可以上个 Q. And second premise, I do not exercise, so not P. What kind of conclusion we can draw that guaranteeing this argument is a valid argument? What do you think? What do you think? Is actually actually you are right. Q is actually Q. My bad. Yeah, let's make sense of it. The first piece says, so if we see not Q as one piece, so Q is feeling energized, then not Q is not feeling energized. And our first premise says the yellow and the green, at least one happened, right? The yellow and the green, at least one happened. And we know now the yellow does not happen. Then the green must happen. Oh, you know what? I was right. Sorry. I was right. Do you see what happened, guys? So let me explain again, okay? Yellow and green, at least one happened. Yellow and green, at least one happened. So I'm going to point this way. Then you can see what I'm talking about. Yellow and green, at least one happened. We now know yellow does not happen. Then green must happen. Because at least one happened, right? If we know if we know yellow doesn't happen, then green must happen. Do you see that? So what reasoning that is? Disjunctive reasoning, right? Disjunctive reasoning, right here. Disjunctive reasoning. Do you see that? Very interesting, right? Yeah, very good, very good. Thank you guys for your response. Do you like this section? The next section, the last section of this chapter, we're going to use a different tool to test the validity of an argument. And we're going to use Euler diagram to test the argument that involves quantified statement. Okay, so I'll see essential in 10 minutes, and the rest of class, I'll see you on Monday. Please feel free to email me if you have any questions. It is a little confusing, but I'll get it. Okay. Because the first time you learn this content, right? You are doing great. You're welcome, Emma. You're welcome, Ashlyn. Okay, guys. I'll see you later. Bye-bye.